Explanation has been a different thing proposed as the hypothesis of the old. Boundless impact, different evaluations besides those made by an immense number of specialists, support this thought, giving attestation about how the universe began. In any case, the current universe of science, with new headways, brings us novel assessments and perspectives. These thoughts challenge our points of view. Sure, pieces of data, such as those from Neil deGrasse Tyson, have turned into colossal figures in this influencing universe of science. Now, something drawing in is happening with the James Webb Space Telescope. It's fundamental to perceive something that could make us question the hypothesis of the universe's starting point. The James Webb Space Telescope has found 750 new universes. These frameworks are not precisely indistinguishable from what we expected, leading us to re-examine what we assumed we had some cognizance of. This discovery should assist us with valuing how gigantic frameworks turned out to be. So, it's not amazing that it's working up how we would have the option to disentangle the universe. Before, specialists said that the Big Bang hypothesis was a remarkable explanation for how the universe began. As per this hypothesis, around 13.8 billion years ago, the universe showed up through a confusing event. Like the insane story of the universe's introduction to the world, the photos from the James Webb Space Telescope have tested this thought. These photos show universes that are more unobtrusive, smoother, and more established. To say the least, not the same as what the hypothesis of how things came to be predicts. As per the speculation, as the universe grows, objects ought to look more observable the farther away they are. Nevertheless, these self-absorbed structures try not to keep that standard. The hypothesis, moreover, states that at the universe's genuine beginning, every one of the matter that makes up the universe was squeezed into a superdense point called a singularity. This singularity was incredibly hotter than anything we could measure or create. This idea of a singularity comes from equations in general relativity proposed by Albert Einstein. Within the singularity, all the stuff in the universe was pressed into a little space with exceptionally high density. In simpler terms, specialists have continuously said that the hypothesis of how things came to be explains how the universe began. However, these new pictures from the James Webb Space Telescope are making us question that thought. The universes it found don't fit with what the hypothesis expected, and the hypothesis clarification of the early universe might not be as strong as we once thought. In our persistent perspective on the universe, we recognize that all the energy in the universe started from an incredibly hot and dense point called a singularity. This point is like the early stage for all that we see in the universe today. After this singularity, the universe began to expand and create over roughly 13.7 billion years to become what it is today. The development began with something numerous scientists call the incredible expansion, where the universe expanded unbelievably rapidly, much faster than the speed of light. The genuine surface of space itself was growing, and everything in it was extending alongside it. This unlimited growth helped shape the universe by making things more uniform, paving the way for galaxies, stars, and other structures to form. As the universe continued to develop, it didn't expand as fast as during the incredible expansion. However, it continued growing in a steady progression. Specialists have seen proof of this increment through observations, like the way light from faraway galaxies shifts in color, known as the redshift. Currently, let's examine those shocking pictures of new galaxies taken by the James Webb Space Telescope. For most, these photographs look stunning with different galaxies in a single frame. However, for scientists, it's generally a shock. These photos don't match what their hypotheses expected. For example, these galaxies are essentially older than anticipated, which challenges our perspective on galaxy formation and evolution. As per the ancient Big Bang theory, there should be significantly more chaotic systems than what was expected. However, the James Webb Space Telescope pictures reveal many more galaxies than guessed. This makes specialists question whether the hypothesis estimates are accurate. Some scientists are even beginning to overcompensate, considering how these discoveries don't align with their ideas. Another surprising aspect of these new structures is their flawlessness, which clashes with what the Big Bang hypothesis proposed. According to the hypothesis, galaxies should display irregularities and complexities in their structures due to how they formed and evolved. Yet photos from the James Webb Space Telescope show galaxies that are incredibly smooth without the expected chaos and turbulence. During the early universe, all the matter was squeezed into a small space. As the universe expanded and cooled, changes occurred in particles like protons, neutrons, and electrons. These interactions played a massive role in the development of matter in the universe. Within the first 2 to 3 minutes after the Big Bang, a process called nucleosynthesis created lightweight elements like hydrogen and helium, laying the groundwork for stars and galaxies. This alarming revelation challenges the idea that chaos is a common part of galaxy evolution. If there are few or no chaotic events, as suggested by the Big Bang hypothesis, it becomes questionable whether small galaxies could grow to become more massive. Additionally, the optical phenomena expected by the expanding universe theory, where objects appear smaller with increasing distance due to expansion, don't seem present in this context. Specialists have noticed a striking example where massive structures tend to cluster together in enormous gatherings, forming networks across the universe. This large-scale structure aligns with the assumptions made by the Big Bang hypothesis. According to the theory, the universe began in a dense state and then expanded and cooled. As the universe expanded, gravity played a huge role in shaping how matter was distributed, leading to the clustering of galaxies and the formation of interconnected structures known as the cosmic web. The presence of these galaxy clusters and the cosmic web strongly supports the Big Bang hypothesis. The hypothesis explains how galaxies are distributed across the universe and aligns with the gravitational effects anticipated from an initially dense state. However, the James Webb Space Telescope's discoveries challenge the specific predictions about the early universe's structure and formation. For instance, galaxies observed in the James Webb images are unexpectedly smooth and symmetrical. This finding raises questions about the assumed chaotic and turbulent early stages of galaxy formation. If these galaxies were formed so soon after the universe's birth, how did they achieve such organized and mature forms? Additionally, the abundance of older galaxies in the early universe contradicts the expected timeline of cosmic evolution. According to the Big Bang theory, it would have taken much longer for galaxies to form and evolve into the structured systems we observe today. This mismatch between predictions and observations suggests that the current model of the universe's origins might require significant revisions. Scientists are now considering alternative explanations or adjustments to existing theories to account for these unexpected findings. One possibility is that our understanding of cosmic evolution and the processes that shape galaxies is incomplete. The mechanisms responsible for galaxy formation and development might be more efficient or rapid than previously thought. Another possibility is that the universe's expansion rate or timeline of events may not align perfectly with the current Big Bang model. These revelations open up new avenues for research and exploration. The James Webb Space Telescope has proven to be a groundbreaking tool for advancing our understanding of the cosmos. With its ability to capture detailed images of distant galaxies and peer into the early universe, it is pushing the boundaries of what we know and challenging long-held assumptions. In the coming years, scientists will likely use the data from the James Webb Telescope to refine their theories and build new models of the universe's origins. While the Big Bang hypothesis remains a cornerstone of cosmology, these new findings highlight the dynamic and evolving nature of scientific inquiry. As we gather more evidence and develop new tools for observation, our understanding of the universe will continue to expand. The discoveries made by the James Webb Space Telescope are a testament to humanity's curiosity and ingenuity, driving us to seek answers to the most profound questions about our existence and the cosmos. Also, growing state is proposed by the hypothesis. These variables, counting the grouping of frameworks, the astronomical web structure, and the spreading of universe groups, give strong proof that the universe advanced from a very thick state and has been extending for billions of years. Currently, we should get back to the size of the designs viewed as by the JWST. These photographs go against what we thought we had some awareness of the Big Bang hypothesis. As indicated by the hypothesis, small universes ought to form and stretch out through impacts and consolidations with other universes. However, the universes made by the JWST feel very different from this thought. Assuming cosmic structures were impacting and converging as anticipated, we would see proof of these crashes or consolidations. Yet the photos show something else. The Big Bang is, too, a hypothesis, essentially a thought without conclusive proof. Nonetheless, it is truly upheld by obvious evidence, including views of the redshift of light, observations from far-off universes, which offer support for the expanding universe hypothesis, studies showing universes increasing their distance from each other, suggesting the expected consistent increment anticipated by the hypothesis, the spread of light elements like hydrogen and helium seen throughout the universe, which is consistent with the theory of the universe's start, the enormous scale distribution of universes as revealed through cosmic outlines, which matches patterns anticipated by the Big Bang theory. One of the fundamental pieces of proof for the Big Bang hypothesis is the discovery of the cosmic microwave background, CMB. The CMB is weak radiation that fills the whole universe and represents the remnant glow of the Big Bang. This significant radiation, first identified in 1965, still aligns with the expectations made by the theory of the universe's origin. The observed qualities of the CMB, its consistency and temperature distribution, strongly support the likelihood that the universe was once in an extremely hot and dense state before undergoing expansion. A central piece of the theory of how things came to be, the discovery of the cosmic microwave background, is a critical piece of evidence. It offers us a fascinating glimpse into the early moments of the universe, acting as a remnant of the initial stages after the Big Bang, and plays a vital role in cementing the hypothesis as our best explanation for the earliest stages of the universe's development. New discoveries challenge the Big Bang hypothesis. However, discoveries have tested several aspects of the Big Bang hypothesis. The presence of universes with ages that seem to originate before the Big Bang conflicts with the theory, suggesting that the Big Bang might not have occurred as initially thought. Additionally, radiation emitted by these newfound universes struggles with what was expected from the Big Bang speculation. This has led many to rethink the theory of how things came to be, particularly given recent scientific advancements provided by telescopes like the James Webb Space Telescope, JWST. The James Webb Space Telescope, JWST. The JWST has caused significant waves in the academic community, prompting a re-evaluation of the well-established Big Bang hypothesis. For over a century, the Big Bang hypothesis has been the prevailing explanation for the origin of the universe, suggesting it began from an incredibly dense and hot singularity roughly 13.8 billion years ago. However, data collected by the JWST has sparked a series of discussions, challenges, and debates among scientists, suggesting that the universe may have evolved in ways previously unknown. These groundbreaking discoveries are not only pushing the limits of our understanding of cosmology, but also driving the need for new perspectives and updated models of the universe's origin. Evidence supporting the Big Bang hypothesis. The Big Bang theory has long served as the foundation of modern cosmology. It suggests that the universe began from an incredibly hot, dense point, a singularity, that then expanded and cooled over time, resulting in the vast universe we observe today. This hypothesis is supported by various key pieces of evidence, including 1. The discovery of cosmic microwave background (CMB) radiation. First detected in 1965, it provided insight into the state of the universe approximately 380,000 years after the Big Bang. 2. The redshift of distant galaxies. Observed by Edwin Hubble in the 1920s, this shows galaxies moving away from us, suggesting the universe is expanding. 3. The observed abundance of light elements like hydrogen and helium. These are consistent with predictions made by the Big Bang theory. Despite this compelling evidence, the hypothesis faces ongoing challenges, particularly regarding the universe's earliest moments, such as the cause of the Big Bang and what occurred during the inflationary period when the universe expanded dramatically in a fraction of a second. Enter the James Webb Space Telescope, JWST. Launched in December 2021, the James Webb Space Telescope is a groundbreaking observatory designed to revolutionize our understanding of the universe. A collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, the JWST is located at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. This location, combined with its advanced infrared capabilities, allows it to observe distant cosmic objects previously inaccessible. The JWST is designed to peer deeper into the universe than any telescope before it, providing insights into the earliest stages of the universe by capturing infrared light. It can observe objects that are too faint, distant, or obscured by cosmic dust for other telescopes, such as Hubble, to detect. By enabling astronomers to study early galaxies and stars formed just a few 100 million years after the Big Bang, the JWST aims to answer key questions about galaxy formation, stellar evolution, and the nature of dark matter and dark energy. JWST findings: a challenge to established cosmology. The observations made by the JWST have revealed some unexpected and puzzling findings. One key revelation is that galaxies in the early universe appear more structured and massive than previously thought, contradicting models suggesting that galaxies initially formed through small, chaotic mergers and grew over time. These galaxies appear to challenge the timeline and formation mechanisms predicted by the Big Bang theory. For instance, some galaxies observed by the JWST seem to have formed only a few 100 million years after the Big Bang. These galaxies exhibit levels of complexity, brightness, and mass that are difficult to reconcile with current theories of galaxy evolution. If galaxies grew primarily through collisions and mergers, we would expect to see evidence of such interactions in these early structures. However, the JWST images show smoother and more orderly formations, raising questions about the processes driving galaxy growth. Additionally, the discovery of stars and galaxies emitting light with redshifts far higher than anticipated suggests that the early universe may have been more dynamic and diverse than previously imagined. These findings imply that our understanding of the universe's early epochs may require significant revision. Reconciling JWST discoveries with the Big Bang theory. Scientists are now grappling with how to integrate these discoveries into the broader framework of cosmology. Several possibilities are being explored. 1. Revised models of galaxy formation. It may be necessary to update current models of galaxy formation to account for the rapid and advanced development of galaxies in the early universe. This could involve re-evaluating the role of dark matter, gas dynamics, and star formation rates during the universe's infancy. 2. Alternative theories. Some researchers are considering alternative cosmological models that could better explain the observed phenomena. These models may challenge the conventional understanding of the Big Bang, suggesting that the universe's origin and evolution are more complex than previously thought. 3. Advances in observational techniques. The unprecedented sensitivity and resolution of the JWST allow it to detect phenomena that were previously invisible. It is possible that these observations reveal previously unknown processes that occurred during the universe's early stages. The future of cosmology with JWST. The JWST is still in its early stages of operation, but it has already provided a wealth of data that is reshaping our understanding of the universe. As more observations are made, scientists hope to answer some of the most pressing questions in cosmology. What mechanisms drove the rapid formation of galaxies in the early universe? Are there previously unknown physical processes at work in the early cosmos? How do these findings align with or challenge the Big Bang theory? What do the properties of these early galaxies tell us about the nature of dark matter and dark energy? In the coming years, the JWST will continue to push the boundaries of human knowledge, offering unprecedented insights into the universe's earliest moments and its long-term evolution. Its findings will likely lead to new discoveries, refined theories, and perhaps even revolutionary changes to our understanding of the cosmos.